as we can see here, like I've said, yes, combining the two like that, our usual thing, this not being equal to 0. So what it means is this necessarily, this comma that should be equal to this rho nu minus the nu that x of x minus the rho equal to that. Well, because I think I'm going to need this due to this contraction here, let me contract this. If I contract, so let me say contracting rho and nu, contracting rho and nu, I'm going to have h prime of sigma, let me call them both sigma. This will be h sigma, sigma minus the sigma epsilon sigma of x minus the sigma, again epsilon sigma of x. Oh well, you can see here that these two are the same. Like we said, when you have two dummy index written in this form, I can as well raise and lower the other one. So whatever form I choose to call that, sigma minus 2 sigma epsilon sigma of x. So in other words, h prime of sigma should be equal to that. So I can box that in somewhere here, saying that h prime of sigma is here equal to h sigma minus 2 here, the sigma epsilon sigma of x. Or if I like, yeah, I can say h sigma is same thing as that, but I don't think if I'll need this anyway. Well, let's just have that on record. So that is that. So the next thing I'm going to try to do is, having obtained this contraction or the expression for this, which is something I would like to write here next, which is that h prime of rho nu is the same thing here as what have we got? H rho nu minus the nu epsilon of rho of x minus the rho epsilon of nu of x. So the next thing is to substitute that into that expression. So I've got everything for the sigmas and all that. So we have stated, first of all, that h mu nu satisfies this equation. Now we want to see if that, or we want to show the condition under which this will have to satisfy the same equation. And in using this, we have sort of raised the expression for that. We've sort of raised the mu to obtain that. So now it's most likely or suitable to substitute that here. In other words, for this left-hand side, so in place of that, because this here is the same thing as the h prime nu rho, the x nu, right? So I'll differentiate this h prime rho. So in place of it, so what I'm going to do is, in place of, well, yeah, in place of this h prime nu rho, I'll simply impute this. So this will be the x nu, this now here, this minus the nu epsilon rho of x minus the rho epsilon nu of x. And this should be equal to, looking at the right hand side, this is half. So I would like to write everything in terms of the unprimed quantity, and the unprimed quantity is given to us by that. So, and that is differentiated with respect to x rho, as denoted here. So this is the x rho, and here in brackets, prime nu is the same thing as prime sigma. So well, let's maintain the nu. So this is nu, for instance. This is nu minus this is 2. Well, nu epsilon nu of x. I guess that is just the same thing as that. Well, there's no big deal here. Yeah. So what do we have here on the left hand side? What we've got on the left hand side, so then to get another marker. Well, what we need to get here on the left hand side here is so I can write this as the nu of h rho nu minus well, this is the x nu, this is another the x nu. Given the fact that these two are joined together like this, you can't have them just on the same side. In other words, both covariant or both contravariant. So I will necessarily have to write one on top and one down. This is rho of x. And now here I'm going to have minus. This is going to be the nu, the rho, epsilon nu of x. And here I'm going to have 1 over 2 of the rho here, h nu minus, it's not going to be, okay, half in this case because these two will cancel that. So I'm going to have the rho, the nu, epsilon nu of x. I'm guessing that's what it should be. Here, at this point in time, I think I'm beginning to have a problem here. If this is not a problem, might not necessarily be a problem, but yeah, it might be a problem. Well, let's see what we've got. I've maintained here, for instance, I came here and I raised this up. Yeah, it's no big deal. It should be the same. And now here I have minus that on the left-hand side. This is the rho, and this is mu. So what I can do here on this left-hand side is, for instance, try to raise and lower. Like I've said, so please, sorry, at this point in time, I think I might have written this in the wrong. Okay, so sorry about that mix-up. What actually happened here was this. I used this expression. This expression here, if you remember, this was exactly what we obtained. Believing it was the same form as this, differentiated with respect to x nu. But if you look closely, you can see that what I actually had on top here is a nu and not a rho, and what is down is rho and not a nu. So I actually interchanged them and went straight ahead to differentiate with respect to x nu. And quite naturally, I did run into a problem here where I already had the nu down here, and I saw that I had to differentiate with respect to x nu, and stated that no, those two shouldn't be the same. Of course, that should have been a signal to me that something was wrong. Because I believe they shouldn't be the same, because that would give me something like, say, the nu, and that wouldn't make sense. Because usually what you have is either the nu, or maybe the nu, and these two will always give us the D'Alembertian. So please, the mistake was in the fact that we had used the wrong expression. This expression should have been written in the form that it will look exactly like this. Then I can go straight ahead and differentiate in respect to x nu. Of course, we will have gotten the same thing if I then differentiated this. If I had differentiated it with respect to x rho, and then the right hand side I'll differentiate with respect to x nu. But to avoid all that confusion and just go ahead with what we've started with already, I rewrote this expression into the form that it should look like. So for instance, this expression here, all I had to do was to interchange rho and nu. Please know that this is not normal and it shouldn't be, it's not a kind of a valid expression if it is not something that simply worked for us in this case, because we know here that rho is a free index, you can see, and nu here. So I just simply made that interchange so that this will look exactly like that. But you can't make that interchange unless it's a dummy index or they are both dummy indices. But this is just me changing one free index to the other to make it look like what I need. Okay, now having written it in this form, then I can go ahead to differentiate with respect to x nu. And you can see that if I substitute this here on the left hand side, and then on the right hand side as expected, for h prime nu, which I've copied the expression here, I'll simply take h prime, instead of sigma, I take nu. So nu everywhere, and that's what I've done, and that's what I have here on the right hand side. And I'm differentiating that with respect to x rho, which is what we've got here. Now you can see quite naturally that this will be differentiating this with respect to x nu, and then here also x nu can come along. But then again, just like what I expected, you can see that this, when combined with this, just gives me what I will expect for whenever I have two such similar indices. So one has to be down and the other one on top. And that again, when I express the right hand side, I open up the bracket, the two cancels that and I get this. Now looking at this expression, you can see that this and this are quite the same. both in expression and their sign. So on both sides of the equation, they cancel out. And what I've got left is simply this, the D'Alembert of that minus. So if I take this to the other side of the equation and bring back this, what I'm going to have is D'Alembert of epsilon. Well, we have here rho of x, and this should be equal to, I can say h nu of rho comma nu. That's what I've got here. And this coming over will be minus 1 over 2h nu comma rho. Okay. This here happens to be a condition. You can see that if this here is exactly equal to that, are you getting me? If this is equal to that, then just as we expected, h prime sub mu nu, which we have rewritten in this form in particular, this in fact also satisfies this expression, just like this does satisfy the expression we have written right from the beginning. Okay, well, that was erased, it's no problem. So, well, another way to write this is this, which then, of course, again, rho here, what have I got here? Nu is no problem, comma nu. So this is comma nu, so which is why this is nu here instead of the rho that I had here. So with this condition satisfied, then this h mu nu prime, just like h mu nu, satisfies the 4 coordinate conditions given to us by the harmonic coordinate conditions, which was the additional sets of equations that we needed in addition to the Einstein field equation, which is just about 6 here, to give us the complete set of equations that will satisfy, that will unambiguously determine or solve this equation completely. And the 2 sets of equation should give us what we are looking for. That's exactly what we've got. Since even though that was deleted, I think I can simply just copy that from here. Instead of the primes, I have rho, comma nu, equal to 1 over 2h. This is nu, comma rho. So, just like in the case, I've erased that already. Just like in the case of Maxwell's equations, I believe what we had then was something like this. In the case of Maxwell equations, we had the Lorentz gauge. Yes, the Lorentz gauge, which was the alpha equal to 0. And then I guess then was alpha here, minus, this was supposed to have been beta. And I'm guessing here, yeah, exactly, this is beta. And the alpha here, A beta, and all of this being equal to minus J alpha. Well, I can't remember, please, if this was exactly correct. Well, the important thing is these 2 sets of equation forms a complete set. And with these 2 sets of equations, as you can see, this is actually 1, and this is 3, like we have explained. This forms a complete set and unambiguously determine A alpha. So this here, the Einstein field equation linearized form, and this one here unambiguously solves the Einstein field equation or obtains the solution for h mu nu. Okay, one very quick, what am I going to say? Yes, exactly. Very quick analysis we can make using this is the fact that given this expression, I can write the Einstein field equation, by the way, in the following form. And what form am I talking about? I'm talking about here the Einstein field equation being this h here, and I have mu nu, minus here h lambda nu, comma here, I believe this is lambda mu, minus this is h lambda mu, comma, what I've got here is lambda nu, and then plus h lambda lambda, and what I've got here is comma mu nu, exactly, and this I said should be equal to minus 16 pi g z sub mu nu. Yeah. So this is what we've done. Now, looking at this expression, I can write this left-hand side as this. This is h mu nu minus, just looking for a way to apply this, I can decide to say, for instance, that this is the same thing as h lambda nu, comma lambda, comma mu. Remember, because this lambda mu means I'm differentiating this object with respect to x lambda, then after, or x mu, then afterwards with respect to x lambda. So I can just say, okay, the first thing is differentiate the object with respect to x lambda, then differentiate that with respect to x mu. It's commutative, by the way, and it's possible. And this again is minus. I can write this as h lambda mu, comma here. What have I got? Yes, another lambda, and then here, comma nu. This is what I've got. I can write that as that. And then finally, I have here plus h lambda lambda, comma mu nu, equal to minus 16 pi g z sub mu nu. Why am I doing this? From this expression over here, you can see that this, for instance, is the same thing as half. Well, ignoring the primes because I'm not working with the primes this time around. I can choose whatever dummy index I like. Looking at this term here, so let me use lambda. So this is the same thing as half h lambda lambda. But then, of course, remember that h lambda lambda. Okay, yeah. Okay, I think I should be looking at the left-hand side here. So please, just this is what I'm looking at. So anytime I have such an object as nu row here, nu, the next thing should be half nu. This could be a dummy index, but the important thing is I'm differentiating with respect to x row. So here I'm differentiating with respect to x mu, x nu, sorry. So you can see I'm differentiating with respect to this nu here. So this object in the bracket is the same as that, and this which is outside remains the same as that. Again, look carefully at this expression. In fact, let me remove the primes. So if I had nu differentiated with respect to nu like this, then the next thing on my right hand side should be equal to half h sum. Like I said, you can choose this to be anything. This is the dummy index. But then the important thing is that it has to be differentiated with respect to x row, which is the only uncontracted index here. My only uncontracted index here is nu. So what I've got is some h lambda lambda, which is a dummy index, and the only uncontracted index is what? Nu. In fact, to avoid confusion, like I said, you might as well call this sigma sigma. The only uncontracted index is nu, and that's why it's differentiated with respect to nu. Meanwhile, my mu is still outside, right? Now this is going to be minus. Okay, let me not do that yet. Now this here in the bracket also is the same as some half. I can call this again h sigma, is sigma, and differentiated with respect to x mu. Again, because mu here is the only uncontracted index in this expression. And from our proof, this is the same thing as some half h sigma sigma, whatever you like, a scalar here, differentiated with respect to x mu. So just like in this case. But then again, our comma nu here is still here outside. Okay, so I want to call your attention to something. Both these expressions have minuses. Okay, well, let me just, I think there's no point. So I can have this to be half, just for the sake of, I can change the sigmas to lambdas, or let us maintain the sigmas. Sigma, sigma, comma. If I'm opening up this bracket, this will be comma nu, mu, right? And then this will be minus again, half, h, sigma, sigma, comma, this is mu, again, mu, nu. Like I said, this is our expression. Okay, apparently in some books, oh yeah, well, our very good friend Joseph Weber in his book, sometimes when he says something like h comma, when we say something nu mu, I think he does something like this, comma nu, comma mu. So in case you find something like this in the literature, just know it means the same thing. But we don't need that here, and well, that is his own way of doing things. I don't find that convenient personally. So here, this is going to be plus. I can change these lambdas to sigma. I want to do that, comma mu nu. This will be minus 16 pi g z sub mu nu. Okay. Now looking at this expression, this is minus half this, minus half that. You can see that this two expression gives me simply minus h sigma, sigma, comma nu mu. So it's just minus plus of that. These two are the same because I'm differentiating this object h sigma sigma with respect to x mu x nu. So it's the same thing as nu x and nu mu. So these two objects here cancel because this is a minus and a plus. So all I'm left with here on the left hand side is this D'Alembert of this equal to minus 16 pi g z sub mu nu. Okay, so please come with me. I don't have time going to look for this now. So you can see what we have just obtained is the fact that with this condition, which we have expressed from this, which we have shown from this expression, that's with this being used in the linearized Einstein fields equation. With this being used here, we have shown that this is, by the way, reduced to be that. It's just equal to that. Now, this reminisces what we've done in classical electrodynamics. Just calling our old friend Jackson. If you look at Jackson's book, for instance, you find that for this expression, for this vector potential, we can get a solution as this being equal to that. So just quite analogously, if we have obtained the linearized Einstein field equation in this form, this solution here, z sub mu nu, just like, this solution or the object h sub mu nu, just like A here, might as well be written to be equal to this equal to that. So it might as well be written as this equal to that, just copying analogously from this. Okay, well, I think that's quite a lot for just single presentation. Hopefully in our next presentation we shall give a summary of all the things we have linearized, and I think we have linearized quite a lot.